Okay, let's dive right into this. Welcome to the Explainer. Have you ever just stared at a coffee mug or a chair and wondered why it behaves so, well, normally? Why don't everyday objects just teleport or exist in two places at once, the way quantum particles do? That is the exact mystery we're unpacking today. We're going to explore the mathematical boundary between the bizarre quantum world and our normal, everyday reality.
Even the absolute pioneers of quantum theory struggled with this transition. Albert Einstein himself expressed a deep disdain for quantum weirdness. He famously called the connection between separated particles spooky action at a distance. He suspected the theory was just incomplete, mainly because it conflicted so heavily with everyday classical laws. But what if this spooky weirdness doesn't just arbitrarily stop at a certain physical size? What if it simply fades away because of the surrounding environment?
And that brings us to Section 1, the everyday quantum mystery.
So we're really talking about the paradox of the macroscopic world. Why don't we see a cat, like the famous Schrodinger's cat, existing in this weird macroscopic superposition of being both alive and dead? Why does quantum mechanics seemingly just vanish when things get big? Now, this isn't just some philosophical debate. It actually leads to a massive question. How do we mathematically test reality? Because we can't just guess where quantum physics ends and classical physics begins, right? Physicists test these boundaries using strict mathematical inequalities. Basically, formulas that draw a hard line in the sand between what is a classical system and what is a quantum system.
And this brilliantly illustrates the difference between two of the most famous tests in physics. On one hand, we have Bell's inequality, which tests quantum weirdness, specifically entanglement, across space, using two separate particles. But on the other hand, we have the focus of our explainer today, the Leggett-Garg inequality, or LGI. Instead of space, Leggett and Garg designed a test to measure quantum coherence across time, using just a single particle. It's essentially testing if a particle remembers its quantum state from one moment to the next.
Let's move to Section 2, Rules of Macroscopic Realism. To really understand how the Leggett-Garg inequality works as a test, we have to look at the two very logical classical rules it relies on. These are the assumptions that perfectly define our everyday, normal reality. Here's the first rule: macroscopic realism. It's the idea that a macroscopic object with distinct states available to it is almost always in one definite state, meaning things actually exist in a specific, definite condition, even when absolutely nobody is looking at them. No superpositions, just regular, predictable reality.
The second rule is non-invasive measurability. This is the assumption that we can measure an object's state without fundamentally altering the state itself or messing with its future dynamics. It's kind of like, think about checking your speedometer. Looking at the dashboard doesn't change how fast your car is currently driving.
Now, if those two classical rules hold true, physicists can calculate a specific mathematical correlation across 4 successive measurements taken over time. This correlation is known as K4. Classical physics mathematically demands that this K4 correlation must stay at or below exactly 2. That's essentially the classical speed limit of reality. But here's the incredible plot twist. If you take a perfectly isolated quantum system, a system that actually plays by quantum rules, it fundamentally breaks those classical assumptions. It completely violates the Leggett-Garg inequality. Because the system can exist in a coherent superposition over time, it pushes that K4 bound all the way up to 2.82.
Which brings us to Section 3, enter the environment.
So if isolated microscopic systems can hit 2.82, what stops our macroscopic, everyday world from hitting that quantum bound? Why isn't everything around us acting spooky? Well, let me introduce you to the ultimate quantum buzzkill, the environment. Real-world physical systems are almost never perfectly isolated. They're constantly bumping into and interacting with their surroundings. And this constant interaction causes energy dissipation and what physicists call phase randomization. The environment literally bleeds the quantum weirdness right out of the system. To actually calculate this, physicists don't just use trial and error. They use some pretty heavy mathematics, specifically the Lindblad master equation. This is a complex mathematical formula used to track exactly how an open quantum system interacts with and loses energy to its environment over time. It's essentially the mathematical map of how quantum properties just kind of fade away into the background.
Section 4, how decoherence suppresses quantumness.
So, decoherence is the technical term for this fading process. It's the exact mechanism where the environment forces a delicate quantum system back into normal classical physics bounds. Let's trace this out on a timeline using intervals between measurements, denoted by the Greek letter tau. Now, if tau is short, meaning measurements happen rapidly, quantum coherence survives. The system violates the inequality and scores higher than 2. But at a medium interval, the environment has time to interact, and decoherence begins. And if you wait a long time between measurements, well, the quantumness is completely suppressed. The system acts totally classical, and that K4 value drops right back down to 2 or below.
Now, what's really interesting here is exactly how the environment does this damping. The Lindblad equation tracks 3 specific damping parameters. Gamma 1 is population relaxation, which is simply the system losing energy to the environment. Gamma 2 is thermal excitation, the system getting bumped around by environmental heat. And gamma 3 is pure dephasing, where the environment just scrambles the quantum phase without even changing the energy levels.
To make sense of all these damping effects mathematically, researchers use something called the MR criterion, which is calculated using a pseudo-density matrix. Look, I know that sounds incredibly dense, but you don't need to do the math. Just think of it as a specialized threshold calculator. It finds the exact moment where environmental interaction permanently kills off quantum coherence, making those Leggett-Garg violations completely impossible.
Let's look at Section 5, Real-World Quantum Transitions.
Because, you see, this decoherence isn't just theoretical math happening on a chalkboard in some university. It's actively being measured and manipulated in modern laboratories right now. Physicists are testing this environmental suppression of quantum effects using 2-level Rydberg atoms inside highly controlled resonators. They're testing it with light, using photonic systems and weak measurements. They're even observing these exact Leggett-Garg violations using superconducting flux qubits, which are literally the building blocks of modern quantum computers.
What this theoretical framework provides is a complete, incredibly practical roadmap for experimentalists. Step 1. You initialize an open quantum system. Step 2. You map the environment using that Lindblad equation and those damping parameters we just talked about. And step 3, you use the pseudo-density matrix to predict the exact bound where the transition to classical reality happens. It tells them exactly what to look for.
Moving to Section 6, the grand conclusion.
So, the crucial point here is that the Leggett-Garg inequality isn't just some abstract philosophical idea about Schrödinger's cat. It functions as a strict operational gauge. It gives us the exact mathematical moment when an environment completely destroys a quantum state, bridging the gap between quantum mechanics and our macroscopic world. Which leaves us with a pretty provocative final thought. If constant interaction with the environment is the very mechanism that forces delicate quantum systems to act normal and classical, is the macroscopic universe around us essentially just one giant, continuous observer? It certainly makes you think differently about the everyday objects around you, doesn't it? Thank you so much for joining me on this explainer, and keep questioning the reality you see every day.